Hi everybody, we're going to continue our discussion about angular size, except this time we're going to connect angular size with distance, and we're going to see how the two play off one another. I've put together another series of fun slides for us to go through, and then I'll end again by doing a demonstration, and hopefully everyone can follow along and try to do it using the angular sizes that we learned with our hands in the previous video. So let's go ahead and jump in with angular size and distance. For this one, I am going to use a model of here we have a cat that is some distance away, just some distance. Let's call it a distance D. Could be 5 meters, could be 10 meters, although that sounds too far away for a cat to be. We want it to be much, much closer, unless you're allergic to cats, of course. But let's just say it's some distance D away. Call it 10 meters. Here we have our person that's looking at the cat, and we'll just assume this is what the cat looks like when it's observed at a distance D. That's how big it appears. Maybe you could hold up your fist and it would be 10 degrees, although maybe you'd hold up your pinky and the cat is just 1 degree in angular size at that distance. It doesn't matter, it has some angular size at that distance. So what happens to the angular size, how big this cat appears to be, what we might call its apparent size, as it moves farther away? And yes, this is as simple as objects are move farther away, something farther away looks smaller and something closer looks bigger. It is that simple, except we're going to put some mathematical legs on it and introduce some new terminology. Hopefully it'll all tie together and it'll all make sense. So what would happen if we say move this cat to be further away? Well, as we move the cat further away, it would appear to be smaller. And if we moved it to be 2 times farther away, twice the distance, so at 2 times the distance, the cat would appear 1/2 the angular size. So if at this distance, the cat had an angular size of 2 degrees in the sky, 2 pinkies next to each other, then at double the distance, it would have an angular size of 1 degree on the sky. Double the distance, 1/2 the angular size. Okay, what happens if we keep going? So this time, let's not double the distance, let's go to 3 times the distance. So now the cat will be 3 times farther away. As it moves farther and farther away, it continues to look smaller. And at 3 times the distance, the cat would look 1/3 the size. You're probably starting to see the relationship here. Double the distance, 1/2 the size. Triple the distance, 1/3 the size. Anybody want to take a guess what's going to happen when we go to, say, 5 or 10 times the distance? So at 10 times the distance, if we were to take this cat and throw it off screen, the cat would appear 1/10 the size. 100 times the distance, it would be 1/100th the size. Okay, so that now we have that nice connection. Make something move twice as far away, it looks twice as small. Move it 3 times farther away, it looks 1/3 as big. 4 times further away, 1/4 as big. I can handle that. What happens in the opposite if we take a cat that's really far away and we move it closer? Obviously, as the cat approaches us, it's coming over for some nice pets. But as the cat is walking up to us, it's going to have a larger and larger angular size. It will appear to be bigger. So as the cat closes the distance to 1/3 the distance, so it'd be 3 times closer. Notice saying 3 times closer is the same as taking this distance and moving it to 1/3 the original distance. That would be the same as 3 times closer. So 3 times closer is the same as 1/3 the distance. So I'm moving the cat 3 times closer. At 3 times closer, 1/3 the difference, the cat would appear to be 3 times bigger. That's great because now we can see that it would work in reverse. That some of this 3 times bigger, move it 3 times further away, it would appear to be the normal size. So this is entirely invertible. All right, so if I were to keep moving this cat closer, so let's say it would get 5 times closer, it'd be right about here, the cat would appear to be 5 times bigger. 1/5 the distance, 5 times closer, 5 times bigger. 1/10 the distance, 10 times closer, 10 times bigger. So that is the simple relationship. Now let's put some mathematical legs on it. And I know I put a table, which nobody likes tables in presentations, but I want to go ahead and give some mathematical legs to this. And I want to introduce us to the terminology to take this intuitive concept and actually describe it with mathematical terminology. So first of all, let's explore this relationship that as something increases, the distance, the thing that we're talking about, the angular size, gets smaller. So as distance increases, angular size decreases. As distance gets larger, angular size gets smaller. And they do it in proportion to, well, they do it as one doubles the size or doubles the distance, you become 1/2 the size. So whenever one thing gets bigger and another thing gets smaller in proportion, we say that they are inversely proportional to one another. And let me say that again, and I'll read this directly from the side. When one thing gets smaller while another thing gets bigger in proportion, we say that those two things are inversely proportional to one another. So the angular size of this ball on your screen, as I increase the distance, I decrease the angular size. And they do so in proportion to one another. What do I mean by in proportion to? So here, in proportion means they change by the same multiplicative factor. So that multiplicative factor stays the same. And this is why I have the table. So I just want to show you that. So let's just take some standard distance, just the distance, same as I have down here. So if I were to move that cat to be 1/2, 0.5 times the distance, half the distance, the cat would appear to be 2 times larger. Notice 1/2, 2. Same factor of 2, 2. But here, multiplied by 2, divide by 2. If it was 1/4 the distance, it would appear to be 4 times the size, 0.25 times the distance. Factor 4, so multiply by 4, divide by 4. 1/10 the distance, 0.1. So divide by 10, multiply by 10. So it appear to be 10 times larger, so on and so forth. And then as things move further away, multiply the distance, it gets farther, 2 times the distance, 1/2 the size. 4 times the distance, 1/4 the size. 10 times the distance, 1/10 the size. 50 times the distance, 1/50th the size. All right, so hopefully that helps you go through this. There is an example in the lecture slides that I want you to go through. It deals with how observing the sun if we were on the planet Jupiter. There will be homework questions about this. I hope this will be one of the discussion sections so we can go over it in detail. I did not want to throw it into this particular video because I think this video is nice and succinct and it gets the point across, and I didn't want to confuse the point. So please go review the lecture slides where I talk about angular size being inversely proportional to the distance, and I provide an example question of how big the sun would appear if we were on the planet Jupiter. Notice that we could then use the same argument. If we know how many times farther away from the sun Jupiter is than the Earth, we knew how big the sun was, its angular size, we could go ahead and figure out how big it would be viewed from Jupiter. All right, thank you for your attention. Hopefully you enjoyed this set of slides, and I will see you in the next video.